Okay, so welcome everyone. Today's speaker is Claire Gasquet, and she's an assistant researcher at UC Berkeley's Space Science Lab, specializing in ionosphere thermosphere coupling. And her work integrates satellite observations with modeling techniques to explore the neutral wind dynamics, ionosphere electrodynamics, and photoemission chemistry. And Claire earned her PhD in physics from UC Berkeley in May 2024, working with advisors Thomas Immel and Stuart Bale. And her bachelor's degree she received in physics and math from Dartmouth College in 2019. And so today she'll discuss the evening solar terminator waves in the thermosphere, neutral wind signatures observed by ICON-MIGHTI. So go ahead, Claire.
All right, thanks so much. Thank you, Nick, for the invitation to be here today, and thank you all for being here. So as Nick mentioned, I mostly study the ionosphere thermosphere interactions. My work ranges over kind of a wide variety of things. Today I'm just going to be talking about one part of it, and that's going to be looking at what are called solar terminator waves in the terrestrial thermosphere. So I'm going to start off by giving a little bit of background and historical context about the solar terminator waves, theories about them, and previous observations. Then the bulk of this talk is going to focus on the results of a study that we published last year, revealing the signatures of these waves in the ICON neutral winds, and in particular showing that the signatures are a lot larger than were previously recognized, and suggesting that they might play kind of an under-recognized role in thermospheric and ionospheric dynamics. And finally, the last part of the talk, I'm going to give kind of a sneak peek at some of the ongoing work that we're doing to better understand both the variability of these waves and then also what effect they might have on the ionosphere itself. Last thing before I get started, I'm happy to make this colloquium a little bit more of a conversation. So please, if you do have questions kind of throughout the talk, I'm happy to take them, especially to clarify anything that isn't completely clear. Although maybe save kind of the longer discussion-based questions for the end, I'm planning to leave plenty of time at the end for questions and discussion. Okay, so without further ado, let's get started. All right. So the solar terminator, right? This is the line that's dividing daylight from darkness. It sweeps through the atmosphere as the Earth rotates. And the orientation and the location of the terminator on the Earth, right, is going to change with the seasons, which you'll see will affect the generated solar terminator waves. The theory of solar terminator waves, it stretches all the way back to the 1970s. This was shortly after gravity wave theory was starting to be more well-developed. So Chimonis and Hines' 1970 paper suggested that we should expect to see gravity waves excited during a solar eclipse due to the time-varying heating profile that would be introduced to the atmosphere. And then it was Beer in 1973 who proposed that there might be a similar effect every day just from the daily motion of the solar terminator itself. So when the solar terminator sweeps across the Earth, it results in changes in the atmospheric temperature and pressure. And Beer argued that those might launch disturbances in the mesosphere and thermosphere. These disturbances are kind of broadly termed solar terminator waves, although it's still kind of an open question exactly how they're formed and where they formed. But the idea in general is that these are disturbances that form near and then propagate with the advancing solar terminator. Subsequent theoretical research into the 70s, 80s, and 90s kind of delved deeper into the theoretical underpinnings of solar terminator waves, generally confirming that the moving solar terminator can generate gravity waves. But the lack of observations in the thermosphere kind of prevented this work from advancing much farther, at least at the time. In the thermosphere in particular, it's very difficult to make the kind of measurements necessary to detect these kind of disturbances, partially due to a general scarcity of measurements. But it's even more difficult because measurements are notoriously difficult to take near the solar terminator, because that's where the atmospheric conditions are changing rapidly, which can have a difficult or a negative effect, I suppose, on instrument performance. So in the early days, some of the debates here were over whether these disturbances might be formed as a result of the heating changes in the middle atmosphere, so where the UV radiation is heating ozone, for example, or up in the thermosphere itself via extreme ultraviolet heating of the atmosphere up there. And obviously, as shown here, right, at different altitudes, the solar terminator is not going to be at the exact same place, right? The sun is below the horizon at different places for different altitudes. And that might offer some clues as to the mechanism if you can look at where these disturbances are. but this wasn't really delved into with any great detail at the time. And in fact, at least in the thermosphere, this problem was kind of put down until the late 2000s when the first observational studies started to come out. So in the ionospheric community, the first observations of ionospheric disturbances attributed to solar terminator waves were published by Galushko et al. In 1998. They were using the Millstone Hill Incoherent Scatter Radar in Massachusetts to detect fluctuations in the electron density at different altitudes, which is what you can see in the figure here. And they were focusing on kind of these fluctuations, these larger fluctuations observed post-sunrise. And they were using observations from multiple radar beam directions to try to deduce the period, the group velocity, et cetera, of these fluctuations. They found periods of about an hour and a half to 2 hours, velocities around 300 to 400 meters per second. And those velocities correspond to the solar terminator's speed at ionospheric altitudes. And furthermore, they found that the propagation direction was perpendicular to the terminator, which is to say that it's either going into or out of the actual region of the terminator. So they suggested that those waves were associated with the solar terminator and thought that it was notable that they saw a much stronger signature in association with the morning terminator compared to the evening terminator. About a decade later, Efremovich made the first measurements of these waves using GPS total electron content. And this is a figure from their paper there. They detected both large scale, so like 60-minute period, and also medium scale, which they defined as about 15-minute period variations that they associated with the solar terminator. But again, they were only associated with the morning terminator. And subsequent ionospheric studies have more or less confirmed the results that you see here. So mainly that waves were associated with the morning solar terminator, and that they tend to have phase fronts that are parallel to the terminator. So kind of either following it and then propagating into or out of that region. Okay, I'm just going to highlight one more of these ionospheric studies. This was actually my impetus for getting involved in solar terminator research in the first place. When I was an undergraduate, I did an RAU program at MIT Haystack Observatory. And as part of my project there, we were actually looking for solar terminator waves in the plasma line data from the incoherent scatter radar. So at Haystack, they have these two incoherent scatter radars. There's the zenith antenna, which always just looks straight up. And then there's the steerable antenna, which you can choose the look direction for that. And so we did an experiment where the zenith antenna was obviously pointing straight up. The steerable antenna was pointing eastward. And we alternated taking measurements between the two. And that's the figure you're seeing down here. These were using the plasma line, this is kind of what the spectrum looks like from the radar. The plasma lines are out here. And this is from the peak of the F2 layer. But so this is measuring essentially the electron density to high precision with these plasma lines. And between the zenith here in blue and the steerable antenna here in red, you can see there are these wave features, and there's a clear delay between them. And so using that, we could deduce the speed of propagation, the direction of propagation, at least whether it's going eastward or westward, etc. And then at the same time, right, we looked at a TEC map of what is the total electron content at the time, looking at the fields of view of both the zenith and then in pink the steerable antennas. The conclusions with this were very similar to those of previous ionospheric studies on these, but in general we found that with this study these signatures seem to be consistent with wind-driven dynamo effects from gravity wave-driven zonal winds. But again, these were only observed in the morning. And although this paper didn't actually get into it, there were sometimes, these signatures were sometimes observed and sometimes they were not observed during the experiments, suggesting that there was a good amount of variability. And it remains a little bit unclear what drives that. But otherwise, again, it was consistent with other ionospheric studies. Phase fronts parallel to the solar terminator, propagation direction was perpendicular to the solar terminator. Okay, so that brings us to the thermosphere. So up until the study that we published last year, only 3 studies had ever reported observations of solar terminator waves in the thermosphere. So using the CHAMP satellites, triaxial accelerometer, Forbes et al. 2008 identified a solar terminator in the thermospheric neutral densities. That's what's here on the left. And they found that those had about a 3,000 kilometer horizontal wavelength, and they had phase fronts that were inclined about 30 degrees with respect to the solar terminator, and also found that they were more pronounced during solstices compared to equinox. Subsequently, Liu et al. 2009, that's this one on the right, confirmed the density solar terminator wave, and they also detected a solar terminator wave in CHAMP's thermospheric cross-track, so mainly zonal east-west winds. And so those zonal winds had comparable wavelength and inclination to the solar terminator as the density terminator wave, and the zonal wind magnitudes were 5 to 15 meters per second. So about 5 to 20% of the total mean solar wind velocity, zonal wind velocity at those times. And then interestingly, both of these studies in the thermosphere concluded that the solar terminator wave was more prominent at dusk than at dawn, which was the opposite result as what the ionospheric community was finding. Most of the wave structures here were appearing on the night side, and they were kind of extending into the sunlit region around the solstices. So there was also a third study, I don't have a figure from that was Vespalova et al. 2016, and they were looking at in situ neutral density perturbations by the Atmospheric Explorer E satellite. And they also found density perturbations with amplitudes of about 2 to 4% associated with the solar terminator wave passage. And so these studies actually, they had different suggestions, both the Forbes study and a subsequent modeling study that the same group did suggested that the origin of these waves was kind of in the lower atmosphere. But the Vespalova study, which I mentioned, suggested that it might be in situ. So there's still argument in the community over whether that's the case. Okay. So once again, there was a bit of a time gap before more progress was made on this, but there were some recent modeling results. This is a figure from Cho et al. 2023. And this is an animation using data from one of Sharon Vadas' papers in 2023. And these all of a sudden were suggesting that solar terminator waves in the neutral winds could have a much more significant impact on equatorial thermospheric dynamics than was previously considered. So this result on the right here is modeling using WACOMX. This is a simulation from October of 2020. And here they essentially identified, you can kind of see the shadow of the terminator. I don't know if it's clear on your screens, but these dotted lines are indicating what were considered terminator waves, and this is on the evening side of the terminator. And so they identified these large amplitude evening solar terminator waves with the phase fronts that are aligned from that northwest to southeast. It's the same orientation as the winter solstice terminator wave observed with CHAMP in the Forbes and the Liu papers. And they proposed that, first of all, these are very large and that they might play an under-recognized role in driving equatorial electrodynamic phenomena like equatorial plasma bubbles. Although, again, there hadn't been any observational evidence to prove or disprove this. And then this is here, I'll just play this animation. This is from the High MCM model, and this is data that was published by Sharon Vadas in 2023. And they identified solar terminator waves with horizontal wind magnitudes of 50 to 100 meters per second in this model. This is a simulation from the 15th of January, 2022. This animation, I'll just go ahead and play it again, is showing the horizontal wind magnitude along with the terminator up at 300 kilometers. And then, we've used a rudimentary algorithm to sort of pick out where this terminator wave is, just to highlight it for you all. And notice, you have this inclination relative to the actual terminator. That was what was pointed out in those observational papers from 2008 and 2009. And which is distinctly different from what folks have observed in the ionosphere, where it's parallel to the terminator. And furthermore, just do it again. I just also want to point out that in this model, it seems like there's a fair amount of variability in the magnitude of this wave, even over the course of a simulated day, right? The magnitude is changing a good amount with either longitude or just daily variability. But just to emphasize this, at least in this model simulation, this is the largest magnitude feature in the neutral winds up at this altitude, at least again in the model run for this day. Some of you might recognize the date that was picked for this, January 15th, 2022. That is the day of the Tonga volcanic eruption that went off. This is actually the background sort of baseline simulation for that day. And so the primary focus for this data was to simulate that event. But the solar terminator wave was surprisingly prominent in the simulation results. And even in the case that actually had the Tonga eruption in it, which is this one, this is the same thing, except now you have arrows showing the actual direction of the wind. You'll see the volcano going off. This is a simulation from the actual Tonga event. These are the gravity waves from that event. Oops. Just stopped responding. But so they noted that the solar terminator wave essentially was interacting non-linearly with the waves from the Tonga eruption, and that it might have, you know, a larger impact on these dynamics than was previously recognized, and might be again interacting non-linearly with other types of waves in the thermosphere. Okay, so that brings us to the work that we did. So for anyone who's unfamiliar, let me just briefly introduce the Ionospheric Connection Explorer satellite, or ICON, which was on orbit from about fall 2019 through the fall of 22, when unfortunately it suffered an unexpected anomaly on orbit and we lost contact with it. But there's still about 3 years of fantastic data available. The goal of this mission was to explore the energy and momentum transfer into the ionosphere from both above and from below, and to sort of understand the balance between those two. Most notably for this study are the measurements of the neutral winds, which are taken with the Michelson Interferometer for Global High-Resolution Thermospheric Imaging, or MIGHTI. So ICON here, it's an equatorial orbiting satellite. It follows about a 27-degree inclination orbit at about 600 kilometers. And it achieves complete local time coverage across those the sampled latitudes every 48 days or so. MIGHTI, there's 2 of them. There's MIGHTI A, which is looking forward, and MIGHTI B, which is looking backwards, both at 45 degrees. And so after 7 minutes, right, MIGHTI A is going to take a measurement. 7 minutes later, MIGHTI B is going to take a measurement of the same volume of space. And using that and assuming that the winds haven't changed too much in that region in that time, we can get a complete vector retrieval of the horizontal winds. And these also do altitude profiles of those winds between about 90 and 300 kilometers. It's measuring this by looking at the Doppler shifts in the oxygen red line and green line air glow emissions to get the horizontal neutral wind profiles. And it does it between about -12 degrees latitude and +42 degrees latitude, at least in its normal operational mode. And so unlike CHAMP, which was making in situ measurements, ICON is remotely measuring the neutral wind altitudinal profiles, which lets us measure the vertical structure of solar terminator waves, if we can see them. And we get daytime wind profiles about every 30 seconds, again, between about 90 and 300 kilometers. The nighttime winds are sampled every 60 seconds at the same altitudes, except at the nighttime, we do have a gap between about 109 and 210 kilometers, where the air glow brightness is not enough to take reliable measurements. So here we're using also the version 5 data, which is available now. And so we get both the meridional north-south and the zonal east-west neutral winds. I mentioned at the beginning that measurements near the terminator are notoriously difficult to make. And even with this instrument right near the terminator, there is a brief, about 5-minute data gap when MIGHTI is switching from day to night mode. And also the wind retrieval algorithm for this is assuming that the atmosphere is spherically symmetric. But obviously this assumption is violated by the rapidly changing conditions near the terminator. So some previous work has done an analysis of how large these errors are. The errors can surpass about 10 meters per second, near 150 kilometers, but above 200 kilometers, the errors are expected to be less than 1 meter per second. And so shouldn't affect the analysis here, especially given the magnitude of these waves that you saw in the modeled results just a moment ago. All right, so let's take a look at some of those results. So because of the significant variations in the solar terminator wave morphology between the seasons, we separated the data into Northern Hemisphere winter, the equinox, and Northern Hemisphere summer. What I'm showing here is from Northern Hemisphere winter. And then for each season, we're including data essentially from about 2 full precession cycles around either the solstice or equinox, which is to say that we're getting the full latitudinal coverage of the instrument and full solar local time coverage, and then averaging data together into these bins that you see here. So we're binning both the north-south and the east-west winds for each season into about 30-minute local time bins and 1-degree latitude bins, and then taking the average value in each bin. And I'm just emphasizing this because I want to note that by averaging over all the longitudes, we are selectively retaining features that are traveling with Earth's rotation, which is to say that we're filtering out all of the non-migrating components here. And so that does also affect our resolution. MIGHTI's horizontal resolution is affected by its integration time, the horizontal field of view, etc. And so each of these bins are equivalent to roughly 850 kilometer resolution. But again, given what the Forbes and the Liu papers found, which was that the scale size was about 3,000 kilometers, that should be sufficient for what we're seeing here. Okay, but just to describe this figure, right, this is looking at the Northern Hemisphere winter mighty meridional winds, so the north-south winds, at about 283 kilometers as a function of latitude and solar local time. And this altitude was chosen just to minimize the data artifacts that we were finding at some other altitudes. The gray shading here, right, is the nighttime region at that altitude. And none of the tides or anything have been removed. There's no filtering beyond the binning and averaging applied in this figure. But I want to point your attention to, right, this evening solar terminator wave, that's this feature here, which is the largest magnitude feature in the meridional winds at this altitude on average, at least at most of the latitudes that we're looking at here. And so even without filtering, right, this is one of the largest features, suggesting that, again, it might play a significant role in thermospheric and ionospheric dynamics. For example, looking at, field-aligned ion drag, interhemispheric transport, that sort of thing. Okay, so breaking this down a little bit more. So we did a tidal decomposition of that figure I showed previously. So this is the figure that we were looking at on the previous slide. And then looking at the diurnal tidal component, semi-diurnal tidal component, and terdiurnal tidal components from these. You can see with the removal of each successive, each additional tidal feature, the solar terminator wave feature is remaining, right? The magnitude is getting less and less with each successive removal, but the feature is still there. And so that suggests that the solar terminator wave has, there's parts of it in multiple tidal components, which is to say that it's not attributable to any individual tide. In the subsequent analysis that I'm going to show, it's going to have the diurnal tidal component removed just for clarity, especially because in the zonal winds, you can't see the feature without removing the diurnal tides. But I just want you all to keep in mind, right, that even in the unfiltered version, this feature is distinct and one of the largest magnitude features that we have. Okay, so then taking a look at this as a function of season, and then also we have the meridional winds here on the left and the zonal winds here on the right, again, after removing that migrating diurnal tide. These black dotted lines are denoting where that solar terminator wave feature is located in each of these, and you'll notice that it's distinct in both the winter time and then the summertime. But in the equinox, there's not really a distinct solar terminator wave feature. So this is really most prominent during the solstices, which is consistent with the results of the previous papers. So the Northern Hemisphere winter solar terminator wave is characterized by about a 50 meter per second northward wind and about a 50 meter per second also eastward wind on the night side. Although the zonal wind component is kind of weaker up here on the day side. It has about a 3,400 kilometer scale size, and it intersects that solar terminator somewhere between 15 and 20 degrees latitude, with again about a 30-degree inclination compared to the solar terminator wave itself. And so a lot of these results are consistent with the features that were seen in the Forbes and the Liu papers, with the difference being that the magnitude is a lot larger here than what was reported previously. For the Northern Hemisphere summer case, MIGHTI's latitude that it samples doesn't reach farther south than about -12 degrees. And so we might expect the Northern Hemisphere summer solar terminator wave to intersect the evening solar terminator wave kind of below what we can observe. But we do observe this about 40 meter per second southward wind enhancement, and about a 25 meter per second eastward wind enhancement, whose phase fronts, when extrapolated down to the lower altitudes, also intersect that evening solar terminator between about -20 and -25 degrees latitude, which is somewhat consistent with sort of the mirror image of the winter case up there. The scale size of the feature is also about 3,000 kilometers, and it's also inclined. This one's about 40 degrees relative to the solar terminator at the intersection point. Let's see. And then again, the combined equinox that you have here, the solar terminator wave is less evident even after removing those diurnal tides. And again, that's consistent with previous studies. So right, we have the winter and then the summer terminator wave. The results sort of mirror each other. They both have those phase fronts inclined relative to the solar terminator, and intersecting it in the winter hemisphere at about 19 solar local time. And the persistent presence of this solar terminator wave in the solstice winds, even with this long-term averaging that's applied, it shows that it's a robust feature. And so while there is likely that day-to-day variability or the even longitudinal variability, like I showed in the model result earlier, the large average magnitude of the solar terminator wave implies that it's a dominant feature in these thermospheric winds, at least under solstice solar quiet conditions, which is mostly what we're looking at here. While it is tempting to quantitatively compare the estimated amplitudes here to the Forbes paper or the Liu paper, I want to caution that each study does use a different filtering method, so it's hard to do a direct comparison. The Forbes paper was applying a high-pass filtering. The Liu paper was subtracting a third order polynomial from the densities, and so it's hard to directly compare the amplitudes. But both the modeling results that I showed were presenting unfiltered simulation results, and so the fact that we're seeing such large amplitudes here and that they were seeing large amplitudes in those models, I think is significant. So then the question became, okay, we're seeing these in the winds. What do the models see? And when we bin them and average them in a similar way, and what can we learn from that? And so that's what this is showing. So here we were looking at some simulation outputs alongside the MIGHTI observations to try to understand maybe what we can about the origin of these features. So this is, again, just looking at the Northern Hemisphere winter meridional winds simulated by 4 different models, all with those diurnal tides removed. In the TIE-GCM run, we can run this either with or without the Huff mode extensions, which is to say input from the ICON winds at the lower boundary. And when we're doing it without that realistic input at the lower boundary, there is no clear solar terminator wave signature at all. And then when you do introduce that realistic lower boundary, which is informed by the ICON data, you do see sort of this weak signature start to appear. It's about 25 meters per second magnitude in the northward winds. In contrast, both the WACM-X and the High MCM simulations exhibit a distinct signature right? That is similar to what we see in the ICON winds. And so the question is, what do WACOM-X and High MCM have that TI-GCM doesn't, that they do a better job at capturing generally the scale size and the phase front inclination and the magnitude of this solar terminator wave. And so one difference, right, is that WACOM-X and the High MCM both include lower atmosphere processes, whereas the TI-GCM doesn't have self-consistent atmospheric processes below its 97-kilometer lower boundary. And then the fact that introducing the ICON lower boundary into the TI-GCM partially accounts for the lower atmospheric effects and sort of does create this signature, suggests that there might be something there, right? Which is to say that the lower atmosphere might play an important role in generating these signatures. So similarly, right, the SD WACOM-X has a parametrization of gravity waves in there. High MCM tries to more or less explicitly resolve some of the gravity waves. And so it's possible that the way these are treating gravity waves also plays an important role in creating these. All right. So one other thing that MIGHTI can do that we couldn't do previously with observations of these is look at the altitudinal profiles of these waves. And so this is taking a look at the altitude structure of, again, the Northern Hemisphere winter solar terminator wave in the MIGHTI meridional and zonal winds, and then also in WACOM-X and the High MCM. And I'm just going to note that we have this gap here just because at night, MIGHTI has a gap between 109 and 200 kilometers. During the day, we do have data there, but in order to remove the tides, we had to black out this whole region. So above 200 kilometers, where that nighttime MIGHTI data is available, we do see the solar terminator wave, and it has apparently a very large vertical wavelength. It's greater than 200 kilometers. And then in this region below 115 kilometers, the solar terminator wave can't really be distinguished from the tides, which are more complex down there and have larger amplitudes. The WACOM-X simulations similarly show kind of a nearly constant phase with altitude above 200 kilometers. And similarly, the High MCM results show these as well. This is just kind of fun. This is an animation of the High MCM results, latitude and solar local time over altitude. So you can kind of see the wave coalescing as you go up in altitude. So at the lower altitudes, which you saw at the beginning of this animation, you see the wind signatures are somewhat chaotic. And then at the higher altitudes, right, where the wavelengths are longer, the vertical wavelengths are longer, you do see this feature really popping out and becoming dominant above 200 kilometers or so. Again, these are just the meridional winds in the High MCM. Okay, so that's it for the results from that paper. We showed that the magnitude is far larger than expected. The first observation of the meridional winds, the first altitudinal observations. This is just the summary from that, and then I'm going to talk a little bit about the ongoing work that we have. So although we did report significant evening solar terminator waves, right, we didn't observe any comparable signature near the morning solar terminator. Both the Forbes paper and the Liu paper also noted that asymmetry. They found that morning solar terminator waves were less well-defined than their evening counterparts. The Liu et al. Paper suggested that it might be that there's larger neutral temperature gradients near that evening solar terminator, and that might, cause wave generation to be more efficient in the evening. Some authors have suggested the opposite, claiming that the morning heating process is more efficient than the evening cooling. So you have a sharper gradient near sunrise, which can produce smaller scale solar terminator waves. But it kind of remains an open question. Both of the modeling papers that I mentioned reported a smaller scale, weaker amplitude terminator wave in their simulation results. And ionospheric studies have also shown sort of that asymmetry. They've shown it more in the morning versus the evening. But it's essentially still an open question why we see that asymmetry between the ionospheric results and the thermospheric results. One potential reason that we didn't see them in the morning terminator waves in the MIGHTI analysis is just that the scale sizes might be very different. With the ionospheric studies, they've reported mostly scale sizes around a few hundred kilometers, which we probably couldn't resolve with MIGHTI, whereas the evening ones seem to be a few thousand kilometers, which would be resolvable. All right, so the question is, right, we have these large amplitude winds in this study, and they might influence ionospheric circulation, again, through ion drag, through dynamo effects. That meridional wind can push plasma along magnetic field lines, which can contribute to interhemispheric redistribution of plasma, and can affect, the plasma density and altitude distribution. And then, those F region zonal winds, when they blow across the westward conductivity gradients caused by the changing solar input, might affect upward plasma drifts, like the pre-reversal enhancement. It might affect equatorial plasma bubbles, all of that. And so everything after this that I'm going to talk about briefly is just going to be some of our planned and ongoing work. As I see it, there's about 3 big questions and a few smaller questions currently surrounding our understanding of these waves. First is the origin, right? Lower atmosphere or in situ, and what specifically is driving their production and dynamics. It's still an open question. Next is their variability. Everything we've looked at in this paper was averaging over multiple years of data and entire seasons at a time. And so no one actually has a good understanding of the variability, although the models are hinting that it might be significant day to day and with longitude. And then also ionospheric effects. Do these affect the pre-reversal enhancement? Do they influence the formation of equatorial plasma bubbles? We don't know yet. But given that they're such large dynamical features, it's important to find out. So we're working on all of these questions. I'm going to ask just please not to take any screen grabs of the remaining slides since these are works in progress. But first on the question of just variability.
Real quick, yeah. Claire, would you prefer this part not to be recorded?
Maybe. Doesn't matter too much.
It's up to you.
No, it's fine. I'll just keep talking.
Okay.
Okay. Well, this is top secret, so don't talk about it outside of this room. No, it's fine. But okay. So the question of variability. Given that the signature that we observed in ICON was so large, and now that we know where to look for it, the question was whether we would be able to extract the wave from individual orbits of ICON. Part of it was that prior to this, it wasn't clear exactly where to look, right? The ionospheric signatures, they sort of follow the Terminator, whereas these thermospheric signatures have that inclination with respect to the Terminator. So at the higher latitudes, right, they might be in advance of the Terminator in the winter and trailing it at the lower latitudes. But so based on those results from the paper that I just showed, we have an idea of where to look for the Terminator wave on each orbit. And so here is a look at that from several successive orbits. So first of all, this shows an example of the solar Terminator wave extraction, where we've taken a single pass of data, I've taken out the diurnal tides, and then this is the feature of the solar Terminator wave in that orbit with the diurnal tide removed. Again, this is the northward winds, and you can see that on an individual orbit, right, this feature is really popping. You can see exactly where it is. These over here are showing orbit-to-orbit variability in the amplitude and scale size of the solar Terminator wind signature. And these are altitude profiles of those meridional winds. And this, I've just applied a rolling average filter just to clarify the signatures a little bit, but I haven't taken out the tides. The blue box in each of these panels is indicating where we would expect to see the solar Terminator wave and how big we would expect it to be based on the results of the study that I was just talking about. And so within that highlighted region, right, and I'm just skipping orbits, this is every other orbit, just so that you can see how it's kind of processing in longitude as we go. But within that highlighted region, right, a distinct solar Terminator wave signature is evident on every orbital pass that you see. but both the amplitude and the scale size of the feature are varying pretty significantly from orbit to orbit. And again, this is all just from a single day. And so this is, again, preliminary work, but this is suggesting that, number one, MIGHTI can see individual solar terminator wave features, and number two, it seems like there is a good amount of variability day to day and even with longitude. And we're working to try to understand and characterize this variability a little bit more. It's a little bit complicated by ICON's precession cycle. So this is looking at essentially how long ICON is spending in the solar terminator wave region as a function of time over its precession cycle. And then also the angle between ICON and the solar terminator wave. And for the most part, there's parts of ICON's, so here this is looking at one of ICON's orbits as a function of solar local time and latitude. And there are parts of the orbit where it's actually really nice and really good to sample the solar terminator wave. And that's what I showed on the previous slide was from one of those regions where we kind of cross perpendicularly across it, spend a decent amount of time in the region and can sample it well. But then there are parts of the precession cycle where we kind of sample along the entire solar terminator wave, right? So the black line and the red dotted lines are showing where we expect the solar terminator wave. The blue line is where ICON is sampling. And so there's parts of the orbit where we're kind of just skating along the whole orbit, which means that we might be able to get a sense of how it's changing with latitude during these, but it'll be a little bit harder to characterize the variability because we're not passing it quite as directly. But anyway, so we're working on understanding how these will affect our analysis of variability. But again, preliminary results show that there is a fair amount of variability and we need to understand what that is affecting. So stay tuned for more upcoming work on this. Let's talk a little bit about the ionosphere as well. And so this is a figure courtesy of Anthea Koster from MIT Haystack. And this is a TEC map over North America during an SSW in 2013, a sudden stratospheric warming event. And they were seeing these large scale TIDs in the total electron content data over North America. And she noted that these look pretty similar to our solar terminator waves that we're looking at. I'll note that this has been filtered slightly differently than what is normally done for TEC studies. Often there's a 30-minute filter that's applied, which just gets you the smaller scale waves, but this has a 2-hour filter on it, so you can start to get some of these larger scale features. And so I was curious whether this lined up with where we would expect the winds to be at this time and local time. And doing that, the red lines are where we expect the wind features to be. The color bar is the change in the TEC, and you can see that they line up remarkably well, where the winds from the solar terminator wave are expected to be and where the observed perturbations in the total electron content are. And so more work needs to be done to see if this is a regular feature or whether this is just happening during this 2013 sudden stratospheric warming event. But the fact that these are lining up so remarkably well is perhaps compelling evidence that solar terminator waves can sometimes at least drive traveling ionospheric disturbances. On top of that, we've taken a preliminary look using ICON's ionospheric ion velocity meter, which measures the plasma drifts. We've taken a preliminary look at whether solar terminator waves might affect the pre-reversal enhancement. And for that preliminary investigation, we were looking at magnetic equator crossings by the ICON satellite during the winter solstice period, so November through January, that were occurring in the evening hours when you would be likely to see that pre-reversal enhancement in the plasma drifts. And for each crossing, we were looking at the maximum vertical meridional wind within that time window as a proxy for the solar terminator wave magnitude. And then also what this plot is showing is the meridional drift, so the vertical plasma drift, essentially a proxy for the PRE. And this is as a function of local time and looking at the strength of that drift. And so we just, as an initial cut, we were looking at times when the solar terminator wave was strong versus times when the solar terminator wave was weak. And we found that under those strong solar terminator wave conditions, the plasma drifts were peaking earlier and exhibiting larger magnitudes compared to the weak solar terminator wave cases. Again, we're working on a more detailed analysis of this to fully understand these results, but the preliminary findings provide potentially compelling evidence of, again, a potential connection between the solar terminator wave and the PRE strength. And then the PRE is known to affect the occurrence rates of things like equatorial plasma bubbles. So this could be significant in that respect as well. All right. I think I'm going to stop there and leave, I think, about 15 minutes or so for questions. Again, you can check out the paper this is based on. We have a lot of ongoing work. Please feel free to reach out to me if you're interested in collaborating on this, or feel free to ask questions now. I do want to emphasize that, again, there are still a lot of open questions in this area, and it's going to take a lot of work to sort of figure out what is causing these signatures and how impactful they really are on the ionosphere thermosphere system. But for now, thank you for your time. And yeah, thanks for coming.
Thank you, Claire. Any questions?
I was just wondering, since you started the talk with a mention of this idea of eclipse-driven waves, is there any evidence that that actually happens?
There have been a couple of studies on that. Yes, most of them have been ionospheric, just because TEC data is a lot easier to look at and it's a lot more readily available. But yes, there are several papers showing sort of bow shock, like, or not shock, but kind of like, you know, waves that are coming off the front of a ship type things off of compared to the solar eclipse spot. But yes, there's preliminary evidence that those exist as well. There's a little bit of evidence that there might be thermospheric winds associated with that, although I think more work would need to be done there as well.
Right. Great talk, by the way. Thanks.
Thank you.
Yeah, I'm curious about the energetics of these things. You know, how much energy is contained? If it were all dissipated, would it impact the thermosphere locally? What's known about how they're dissipated? Or is it like a gradual decay? Or do they break and form turbulence, go into smaller scale structures? Maybe that's hard to get at with the sort of resolution you're using with ICON, but it may impact the thermosphere and ionosphere, which may dissipate the structures differently.
Absolutely. That's a really good question. And I would say that that's probably one of the open questions right now. Without a firm knowledge of the origin of these, it's a little bit hard to understand, you know, exactly how they're being formed and how they're dissipating. If you know they're gravity wave related, then we might be able to determine the gravity wave momentum flux if we have an idea of, you know, the scale, et cetera, of the gravity waves. But as of right now, I don't have a good understanding of the dissipation mechanisms or how it's depositing energy into the thermosphere. But that is definitely something that should be looked into.
Okay. Thank you.
Thanks.
Have you compared to any imager data, picture images? And I'm asking because I wonder if there's any ripples that can be observed from that imaging.
Video was a little quiet there. I think you're asking about whether we've compared to imager data. Is that right?
Yes.
Okay. The answer is no. We haven't taken a look at this in imager data yet, but if you want to collaborate about it or take a look at it, I'm happy to talk about it.
Thanks.
So just curious, so the solar terminator is always there. So is the solar terminator waves also always there, just difficult to distinguish from other waves or to detect that? Or it also has certain other conditions need to trigger the wave?
So that's a good question, and that kind of gets at what I was talking about the variability of the waves. So yes, although the solar terminator is recurring every day, there seems to be evidence that these waves, the strength is not always the same. Especially in the ionospheric studies we did, sometimes the waves were there, sometimes they weren't there. In this thermospheric study, it's clear that at least on average, it is always there, and it is one of the strongest features in the thermosphere. But like I said, preliminary evidence is suggesting that there's a good amount of variability, and what is driving that variability is currently unknown.
Thank you.
So is the seasonal variability, you talked about them related to the seasonal variability of the density of the thermosphere? Do you think that that's explaining it?
So it's strongest during solstices as compared to equinox. But we see it in both hemispheres during the solstices, right? It's not just limited to the winter hemisphere or the summer hemisphere. And so it's more likely to be related to the way sort of the inclined, sort of the inclination of the heating. The fact that during the summer or during the solstices, right, you have this sort of inclination in the heat in the terminator with respect to the Earth, whereas at the equinox, it's more straight up and down, which might cause some sort of destructive interference, or maybe the background winds are filtering out this feature, something we're still looking into. But because you do see it in both hemispheres during the solstices, I think it's unlikely to do with the density difference.
Claire, I have a question. So the meridional wind, for example, is showed here.
Yes.
Is this just the speed, or it's just means northward around the equator? I mean, it's not the equator, the terminator.
This is the velocity of the meridional wind with the diurnal tidal component removed. It's northward around the terminator. Yes, I think. Sorry, can you clarify your question?
Yeah, that's what I was wondering. It seems if it's always northward, it seems that it's always blowing from the day into the night. Is that the
Yeah,
what you're seeing?
let me back up and show you just hang on. Sorry for committing here we go. Yes, in the wintertime, it's always northward, regardless of the hemisphere. In the summertime, it is southward, again, regardless of the hemisphere. And so, yes, it is always blowing sort of up into the night side directionally. Right, in the winter, it's north and east, right? So it's kind of blowing up. The direction is up into the night side. In the summer case, it's southward and eastward. So again, blowing sort of into the terminator.
And in the model or icon, do you see the the zonal component too?
The model is consistent with these results, yeah.
So they're always in the zonal direction. It's always kind of eastward. Is that the case?
That's correct, yes.
Okay. And they are
Right,
always
but the
tied
meridional
to-
component changes. Sorry, go ahead.
Oh, they're always tied to the terminator, right? You don't see like wave peaks away from the terminator. You only see this peak kind of attached to the terminator.
So it's propagating at the same velocity as the terminator. Yeah, so it's a migrating feature. Even though, right, as you can see here, it's, for example, in the winter hemisphere at the higher latitudes, the feature itself comes in advance of where the terminator is, but it's still propagating at the same velocity as the terminator.
Well, thank you.
So Claire, so the meridional wind and zonal wind are off phase during summertime and they in the same phase in the winter time, and that's simply because of the shape of the terminator.
Sorry, can you repeat the question? It was a little hard to hear.
If you look at the dashed lines, the zonal wind, meridional wind are in the opposite phase in the summertime, and they're in the same phase in the winter time. Wonder the reason.
It's I think it's less that they're in and out of phase and more just that the direction is changing. In the winter time, the meridional component is northward, and in the summertime, the meridional component is southward. So they're more or less the mirror image of each other in that case, but in both cases, they're eastward blowing into the night side.
Right, yeah, so I was just curious if you relate this to the eclipse waves. Does that also determine the direction of the eclipse waves as well? I mean, for eclipse, it has different paths, so you can sort of predict the direction of terminator waves.
Right, so for the eclipse, we don't have good neutral wind data showing the direction of those wave features. There might be modeling results that I'm not aware of that have looked at that, but that's not something that we've looked at here.
Any last question for Claire? I guess not. So thank you again, Claire.
Yeah, thank you all.